Hello, everybody, and welcome to the first in what we hope is the series of highlighted projects from Digital Works portal. Recall, they're going to be part of the newsletters, and recall that you can self-promote and tell us, hey, we would like our project to be highlighted. So I will first introduce our Digital Works portal crew, Javier Santos, Anuradha Radhakrishnan, Ankita Singh. So you probably know them from their digital signatures, and we are missing Hassan Khan. And my name is Masha Pradanovic, and we are very pleased to welcome Dr. Hailun and Dr. Meckel from Bureau of Economic Geology at the University of Texas at Austin. So with those initial introductions out of the way, I will let Dr. Ni briefly highlight her project and play some exciting videos for us, and then we will follow up with questions.
All right, so let me start sharing my screen. All right. Okay, yeah, so today I just want to briefly highlight this data set that we posted on the Digital Rock portal. And the data set name is a drainage experiment in an intermediate scale beadpack. So first, just some motivation for conducting this experiment and producing this data set. And the overarching question that we want to answer is how much CO2 can be trapped along the way when the CO2 plume is migrating from the injection well all the way to the trap. So as we know, in CO2 geologic storage, after we inject CO2 underground, it's going to migrate upward under gravity through the aquifer. And plenty of past research has shown that small-scale capillary heterogeneity can have a significant impact on not only the CO2 saturation, but also CO2 residual trapping as the plume migrates through. And this in turn then affects how fast the plume is migrating and also the ultimate plume migration extent. And a lot of research has been focused on this near injection well region where the CO2 plume migration is controlled by the injection pressure gradient. And CO2 is flowing in this compact flow style. But for us, we want to focus more on the region that's away from the injection well and where the CO2 plume migration is controlled much more by the buoyancy forces. And the migration path of the CO2 is in this capillary channel flow type of flow path. So in order to better quantify how different degrees and types of small scale capillary heterogeneity affects CO2 flow and trapping in this particular flow regime, we conduct quasi 2D intermediate scale beadpack experiments. And one major advantage of conducting such experiments is that we have full control over the degree and also the type of capillary heterogeneity that we can build into this sand tank or this beadpack. And for example, for this particular experiment, we have two very simple capillary barriers here. You see one at the bottom and one at the top. And these capillary barriers are built with glass beads with just slightly smaller grain diameters than the glass beads that make up the rest of the domain. And so here I'm going to start this little video to show you how this experiment goes. So here we see that non-wetting phase is entering the domain from the bottom inlet, and now it's migrating along the slope of the bottom capillary barrier, builds up column height, breaks through, and then now it's doing the same thing in the upper capillary barrier region, and eventually it breaks through the entire domain. Usually when you're doing a simulation with invasion percolation, this is where the simulation stops. It's when the non-wetting phase breaking through the domain. However, in this experiment, we can see that actually a lot of things are still happening even after the domain has been broken through. And here we see a new finger flow path is established. And after the establishment of this new finger flow path, we see that the non-wetting phase is now coming out of the lower capillary barrier region in these distinct gulps or pulses. And as the pulses go through the domain, we can see that with each pulse, actually slightly more pore space is invaded by the non-wetting phase. And as these pulses keep going through the domain, we can see eventually right here, we actually see this unexpected early breaching of the upper capillary barrier by the non-wetting phase. So here, so the more non-wetting phase is flowing through the domain. And let's see, right around here, we see that new finger flow path has been established right here. And if you just wait a little bit, then you will see another one, a new finger flow path established right here. And with the establishment of these two new finger flow paths, actually now we can see that strong pulsation behavior has stopped. So it looks like nothing much is happening during this phase of the video, but in fact, still more non-wetting phase fluid is flowing through the domain, entering from the bottom and leaving at the top. It's just that with these new finger flow path, the pulsation behavior that we previously saw has stopped. So the video keeps going, but I've already shown you the most exciting part of this experiment. So some main conclusions for this data set. As we have seen, even small grain size differences, as is used in this experiment, can in fact form effective capillary barriers. And in the presence of these capillary barriers, non-wetting phase fluid, such as CO2, can in fact demonstrate these distinct pulsation behavior, as we just saw in that experimental video. And these flow pulsation behaviors can actually cause CO2 to breach these capillary barriers before flowing around and bypassing them. And this is, in fact, a very interesting flow phenomenon that has not been previously shown in experiments to the best of our knowledge. So I'm very excited about being able to observe such a phenomenon. And currently there is a manuscript associated with this data set that is in review. So thank you very much. Now I'm ready for any questions you have.
Thank you very much. And I would just like to remind everybody that in both the raw data as well as this video is posted on Digital Rocks portal project page for this, and there's related publication that will be updated as this great paper goes through the review. Are there any questions from our curators?
I have a question. First of all, that was a really interesting video clip, Hailun. And being an experimentalist myself, I'm aware that experiments don't always go as per our plan. So my question to you is, were there any unexpected observations during an experiment?
Yes, for sure. So when we first started this experiment, so yeah, I was just trying to, test out what flow behavior you will observe with just two very simple capillary barriers. So the simplest type that you can build with such a Sentang beadpack device. essentially. And what we saw actually did surprise us. So first is this pulsation behavior. So I did some literature review, and apparently this type of behavior was observed before, but very few paper has actually been published on this kind of pulsation behavior. And I think it's actually very interesting because before, it has never been observed that the pulsation can actually cause this, this breakthrough right here. And this is definitely quite unexpected for sure. And I think that's the beauty of conducting experiments, because such behavior you actually cannot really see in simulator. But then doing experiments like this can inform us what simulators are lacking when they're trying to simulate real physics. So yeah, this is, I think, what makes doing experiments very exciting for me.
So this is also invitation out there for dynamic modelers to come to this data set to compare. Any other questions?
Yep, from me. Thanks, Helen. Yeah, it was a really cool video. Must have taken a lot of effort to do this experiment and a lot of repetition as well. But yeah, I think more from taking the second step from what Anu mentioned, like when you were doing the image processing, what sort of challenges did you face? And if you could highlight those for us, please. Thank you.
Yes, so for image processing, first I'd like to mention that all of the image processing for this data set is done in MATLAB. But the main challenge for image processing is that for this type of beadpack experiments, in order to calculate CO2 or the non-wetting phase saturation, we have to actually take reference images, first of the dry beadpack and then of the wet or fully water saturated or fully wetting phase saturated beadpack, and then align those reference images with the experimental images in order to calculate pixel-wise CO2 saturation. And in order to do that, image registration is very important in making sure that each pixel actually align perfectly with each other so that the CO2 saturation can be as accurate as possible. But during the experimental procedure, as we're filling up the beadpack with the wetting phase, in fact, you observe a slight compaction effect near the top of the tank, and that deforms the beadpack a little bit compared to the dry reference image. And that's why image registration is very important. And in fact, you can use any software for that, but it's just that in this case, we're using MATLAB. But once you solve that problem and make sure that all your images are perfectly aligned, then yeah, you can reduce the error in the calculated CO2 saturation value as much as possible.
Great, thanks. Yeah.
Fantastic. I also don't want to neglect the presence of Dr. Meckel, that's here with us too. He's a world-class researcher in CO2 sequestration, and he has a center here at the University of Texas and the Bureau of Economic Geology. So, Dr. Meckel, if you would like to tell us a little bit more about all the cool research besides these pore scale studies that you do, that will be fantastic.
Sure. So the tank experiments that Hailun has been working on are an extension of a longer term PhD project that worked through all of the initial phases of how to develop the sand tank and how to work with surrogate fluids at room temperatures to simulate subsurface conditions. And one of the things we really like about this tank is that you can visualize a lot of things that are happening in the buoyancy or capillary flow regime that are otherwise very hard to visualize at a scale. She may not have mentioned this is about a 60 centimeter tank on a side. So these are much larger than core and certainly much larger than any sort of core plug or thin section type work you might do. So really representing macro scale behavior, but really interesting to watch it and document it. There's obviously a lot of quantification that goes along with this. And really, the point of this is twofold. One is to understand the saturation that we expect in clastic materials when CO2 migrates through them. That saturation is then used to estimate the total storage capacity in a specific geology. So we like having some ground truth for understanding what saturations we might expect in these capillary dominated flow regimes, which we think will be the majority of the storage domain largely. So, and then secondarily, I have a second interest in this, and that is we use seismic techniques to image subsurface CO2. And I operate a seismic system, and we're always asking ourselves the question of, well, what do we think we can resolve from a remote sensing capability? A lot of that has to do with the saturation that results in the rock. So we know that the seismic response is dependent on the saturation. So these experiments don't give us direct insight into the seismic response, but they do give us an insight into the saturation, and therefore what we would calculate to be a seismic response from a rock that's saturated, say, in this type of manner. So otherwise at the center, we're generally involved with field scale demonstration projects, and also a lot of regional characterization in the subsurface. So we like to take these ideas and incorporate them in our field work, and also in understanding what regional capacities we might have for CO2 storage. So that's part of what the center does. And then we have about 6 or 7 other people that work on either shallow groundwater monitoring or petroleum engineering and reservoir simulation, et cetera. Hailun didn't mention, but we do actually pair these experiments with dynamic flow simulation, and we have had quite a bit of success matching these kinds of flow experiments to simulations at native scale. So pretty exciting. So that's a lot of, or at least one piece of what our center does.
Excellent. Thank you very much. So if I can just ask Hailun if you could turn off your slides so we can just wrap this up, and I can do a gallery here for the last wrap up. So thank you very much for presenting here. I hope you can also, there's actually quite a number of CO2 projects that are on Digital Rocks portal that are on the pore scale that are obviously complementary to the scales that you are tackling in your lab. So I invite you to check the Digital Rocks portal, and I invite everybody else to check out both this project and the Gulf Center link that we are going to provide together with this newsletter. So thanks again, and see you soon again. Thank you.
Thank you.